Hello there, fellow dreamers, and welcome to another gentle journey with the Sleepy Astronaut, where we drift through the cosmos of curiosity and let wonder carry us softly towards slumber. Tonight we're embarking on a particularly magical voyage, one that takes us not to distant galaxies or alien worlds, but to the invisible ocean that surrounds us every single day. We're going to explore the grand theatre of weather, that ever-changing dance of air and water that paints our skies and shapes our world. Before we float away into the mysteries of clouds and storms, I'd love to know where you're listening from tonight and what's happening in your patch of sky right now. Are you watching rain streak down your window? Is there a gentle breeze rustling through your curtains? Or perhaps you're somewhere where the air is perfectly still, holding its breath like the universe itself is settling in for the night. If this peaceful exploration helps you unwind after a long day, I'd be ever so grateful if you'd give the video a gentle like and maybe subscribe. It helps this little corner of cosmic calm reach other weary travellers who might need a soothing pause in their day. Now, I do hope this isn't so fascinating that it keeps you awake, but if it does, well, at least you'll drift off knowing a little more about the invisible forces that cradle our planet. So settle in, let your thoughts slow like settling dust, and let's begin our exploration. Because somewhere between the breath you just took and the dreams waiting to embrace you lies the extraordinary story of how weather works and why it happens. Weather, when you really think about it, is one of the most intimate forces in our lives. It touches your skin every time you step outside, fills your lungs with every breath, and whispers its moods through the rustle of leaves and the patter of rain. Yet for something so personal, so immediate, weather operates on a scale that's almost incomprehensibly vast. It's a symphony played by an entire planet with movements that span continents and rhythms that pulse with the very heartbeat of our world. Picture, if you will, our Earth as a great spinning marble suspended in the endless black of space. The sun, that distant nuclear furnace, bathes one half of our marble in golden light while the other half rests in shadow. But here's where the magic begins. The sun doesn't warm our planet evenly. The equator, that invisible belt around Earth's middle, receives the most direct sunlight and grows warm, while the poles remain cold and distant from the sun's embrace. This simple fact, this gentle inequality of warmth, is the engine that drives every weather pattern on our planet. Imagine the air around us not as empty space, but as a vast, invisible ocean. This ocean of air, our atmosphere, is constantly in motion, stirred by the uneven heating of our planet. Warm air, being lighter, rises like a balloon filled with hope, while cooler air, being denser, sinks like a gentle sigh. This creates currents, flows and streams in our atmospheric ocean, much like the currents that move through the seas below. The atmosphere itself is a marvel of layers, each with its own personality and purpose. The troposphere, where we live and breathe, extends from the ground up to about 6 miles high. It's here that all our weather happens, in this thin skin of air that clings to our planet like a whisper. Above that lies the stratosphere, home to the ozone layer that protects us from the sun's harsh rays. Higher still are the mesosphere and thermosphere, realms so remote they seem almost mythical, where the air grows thin enough to see the stars even in daylight. But let's return to our cozy troposphere, where the real drama unfolds. The air here is never still, never truly at rest. It's constantly seeking balance, trying to even out the differences in temperature and pressure that the sun's uneven heating creates. Hot air rises from sun-baked deserts and tropical seas, while cold air flows down from mountain peaks and polar regions. This creates a global circulation system, a planetary breathing pattern that moves heat from the warm equator toward the cool poles. The rotation of our Earth adds another layer of complexity to this atmospheric dance. As our planet spins, it deflects the moving air in a phenomenon called the Coriolis effect. In the northern hemisphere, this deflection curves air to the right, while in the southern hemisphere, it curves to the left. This spinning motion helps create the great wind patterns that girdle our globe, the trade winds that once carried sailing ships across oceans, and the jet streams that modern aircraft ride like rivers in the sky. Now, let's talk about water, that most magical of substances. Water covers more than 70% of our planet's surface, and it's constantly evaporating, turning from liquid into invisible vapor that rises into the atmosphere. This process, driven by the sun's warmth, is like the earth exhaling moisture into the sky. The warmer the air, the more water vapor it can hold, like a sponge that grows more absorbent as it heats up. As this moisture-laden air rises, it begins to cool. And here's where something wonderful happens. Cool air can't hold as much water vapor as warm air, so when the air cools enough, the invisible vapor begins to condense back into tiny droplets. These droplets are so small they can float in the air, and when billions of them gather together, they form what we call clouds. Clouds are perhaps the most poetic aspect of weather, those cotton ball sculptures that drift across our sky like thoughts across a dreaming mind. They come in countless forms, each with its own story to tell. There are the high, wispy cirrus clouds made of ice crystals so delicate they seem painted with a feather brush. There are the puffy cumulus clouds that children see as animals and castles, fair weather friends that dot summer skies. And there are the towering cumulonimbus clouds, the titans of the sky that can stretch from near the ground to the very edge of the troposphere, brewing storms in their dark hearts. The formation of clouds is a delicate dance between temperature, humidity, and pressure. When warm, moist air rises and cools, it reaches what meteorologists call the dew point, the temperature at which water vapor condenses. This usually happens when air is forced upward by mountains, by colliding air masses, or simply by the warming of the ground on a sunny day. The rising air expands as it climbs higher where the pressure is lower, and this expansion cools it down, just like when you release air from a bicycle tire and feel it grow cold. But clouds don't just form anywhere. They need something to condense onto, tiny particles called condensation nuclei. These might be specks of dust, pollen, or salt from ocean spray. Without these microscopic seeds, water vapor would have nothing to cling to, and clouds wouldn't form at all. It's a reminder that even the grandest weather systems depend on the smallest details, the invisible architecture of dust and droplets that makes our atmosphere come alive. When these cloud droplets grow heavy enough, they begin to fall, pulled by gravity's gentle insistence. But their journey to the ground is far from straightforward. Tiny droplets might evaporate before they reach us, returning to vapor in the warm air below. Others might collide and merge with their neighbours, growing larger and heavier until they can no longer stay aloft. This is how rain is born, from the marriage of countless water droplets in the nursery of clouds. The type of precipitation we receive depends on the temperature of the air through which the droplets fall. If the air is warm all the way down, we get rain. If it's cold enough, we get snow. Those delicate ice crystals that form when water vapor freezes directly onto particles in the clouds. Sometimes droplets freeze and thaw repeatedly as they fall, creating sleet or freeze after hitting the ground, creating the treacherous beauty of freezing rain. Temperature itself is the conductor of this atmospheric orchestra, and it varies not just from place to place, but from moment to moment. The sun warms the Earth's surface during the day, and this heat radiates back into the atmosphere, warming the air above. But at night, when the sun's warmth is absent, the ground cools, and so does the air touching it. This daily rhythm of heating and cooling creates its own weather patterns, from the gentle evening breezes that flow from warm land to cooler water, to the morning mists that form when cool air meets warm ground. Pressure, too, plays its part in this grand performance. Air pressure is simply the weight of all the air above pressing down on us. When air warms up, it expands and rises, creating an area of lower pressure. When air cools, it contracts and sinks, creating higher pressure. These pressure differences drive the winds that carry weather from place to place, like invisible rivers flowing across the landscape. High pressure systems, or anticyclones, typically bring clear skies and calm weather. The sinking air in these systems suppresses cloud formation, creating those perfect days when the sky is a flawless blue dome. Low pressure systems, or cyclones, are the troublemakers, the storm bringers. The rising air in these systems encourages cloud formation and precipitation, creating the grey, unsettled days that make us want to curl up with a warm cup of tea. The boundaries between different air masses create some of the most dramatic weather on our planet. When a mass of warm air meets a mass of cold air, they don't mix easily. Instead, they form a boundary called a front. Along these fronts, the contrasts in temperature and humidity create instability, rising air, and often stormy weather. A cold front where cold air pushes under warm air can create a line of thunderstorms as the warm air is forced rapidly upward. A warm front where warm air gradually overrides cold air tends to create more gentle, widespread precipitation. But weather isn't just about the immediate dance of air and water around us. It's connected to vast global patterns that can influence our local weather for days, weeks, or even months. The jet stream, that river of fast-moving air high in the atmosphere, can shift north or south, bringing Arctic cold to unexpected places or allowing tropical warmth to penetrate farther toward the poles than usual. Ocean currents, too, play their part, carrying warm water from the tropics toward the poles and cold water in the opposite direction, moderating temperatures and influencing weather patterns across entire continents. There are also periodic oscillations in global weather patterns that can reshape entire seasons. El Niño and La Niña, those mysterious siblings of the Pacific Ocean, can alter weather patterns across the globe, bringing drought to some regions and floods to others. These phenomena remind us that weather is not just local, but planetary. A vast interconnected system where a change in ocean temperatures off the coast of Peru can affect whether it rains in Australia or snows in Europe. As we drift deeper into our exploration of weather's mysteries, we begin to see that what we experience as a simple, rainy day or a beautiful sunset is actually the result of countless interconnected processes, each one as elegant as it is complex. The air that fills your lungs right now has travelled perhaps thousands of miles, carrying with it the memory of distant seas and foreign shores. The clouds that drift past your window are temporary sculptures, constantly forming and dissolving in the grand gallery of the sky. Weather is, in many ways, the planet's way of breathing, of moving and mixing and finding balance. It's a reminder that we live not on a static rock floating in space, but on a dynamic, living world that's constantly changing, constantly in motion. Every breeze that touches your face, every drop of rain that falls, every snowflake that dances in the winter air is part of this vast, intricate system that connects every corner of our planet. So, as we continue our gentle journey through the realm of weather, remember that you're not just learning about atmospheric science. You're discovering the secret language of the sky, the invisible forces that shape our world, and the beautiful complexity that surrounds us every moment of every day. The next time you step outside, you'll be walking into a three-dimensional ocean of air, a realm where invisible currents carry the breath of distant places, where droplets of water dance in the sunlight, and where the very air itself tells the story of our planet's endless, ever-changing moods. And now, as we float deeper into this atmospheric ocean, let's explore one of weather's most dramatic performers: the storm. Storms are weather's way of releasing the tremendous energy that builds up when different air masses collide, when temperatures contrast sharply, or when the atmosphere becomes unstable. They're nature's way of restoring balance, though they often do so with spectacular displays of power that can humble even the most confident observer. Picture a summer afternoon when the air grows heavy and still, pregnant with possibility. The sun has been beating down on the earth all day, heating the ground until it radiates warmth like a vast, invisible campfire. This heated air begins to rise, carrying with it moisture from lakes, rivers, and the countless exhalations of plants. As this warm, humid air climbs higher into the cooler regions of the atmosphere, it begins to cool and condense, forming what meteorologists call cumulus clouds. But sometimes conditions are just right for something more dramatic. When the air is particularly unstable, when there's a strong contrast between warm surface air and cold air aloft, these innocent cumulus clouds can grow into towering giants. They stretch upward like nature's skyscrapers, sometimes reaching heights of 40,000 feet or more. These are the cumulonimbus clouds, the architects of thunderstorms, and they're among the most impressive structures on our planet. Inside these towering clouds, a fierce battle is taking place. Updrafts of warm air clash with downdrafts of cold air, creating turbulence that would make the most hardened pilot queasy. Water droplets are swept up and down in these vertical currents, colliding with each other, growing larger, sometimes freezing into hail only to melt and freeze again. This constant motion, this churning dance of ice and water creates electrical charges that build up like static electricity in a wool sweater. When these electrical charges become too great to contain, they leap through the air in brilliant channels of light we call lightning. Lightning is essentially a giant spark, a momentary bridge between areas of different electrical charge. It can jump from cloud to ground, or even from ground to cloud, following the path of least resistance through the air. The temperature of a lightning bolt can reach 50,000 degrees Fahrenheit, 5 times hotter than the surface of the sun, though it lasts for only a fraction of a second. The thunder that follows is the sound of air expanding explosively as it's heated by the lightning. Light travels much faster than sound, which is why we see the flash before we hear the rumble. You can estimate how far away lightning struck by counting the seconds between the flash and the thunder, then dividing by 5. Each 5-second count represents roughly 1 mile of distance. But thunderstorms are just one type of storm in weather's vast repertoire. There are also the gentle, soaking rains that can last for days, the kind that make you want to curl up with a book and listen to the steady patter against the windows. These usually come from weather systems called low-pressure areas, where air is slowly rising over a large area, creating widespread clouds and precipitation. Then there are the winter storms, those grey sky visitors that transform the landscape with their cargo of snow and ice. Snow forms when water vapour in clouds freezes directly into ice crystals, bypassing the liquid stage entirely. Each snowflake is unique, a tiny frozen mandala created by the specific conditions of temperature and humidity it encountered during its formation. The intricate patterns we see in snowflakes are the result of water molecules arranging themselves in hexagonal structures as they freeze, creating an infinite variety of 6-sided designs. Blizzards are winter's most dramatic performance, combining heavy snowfall with strong winds to create conditions that can make the familiar world disappear in a whirlwind of white. The wind doesn't just accompany the snow, it shapes it, creating drifts that can bury cars and buildings, sculpting the landscape like an invisible artist working with frozen water. And then there are the great cyclonic storms, the hurricanes and typhoons that represent weather at its most awesome and destructive. These massive spiral storms begin as tropical disturbances over warm ocean waters, where the heat and moisture provide the fuel for their development. As warm, moist air rises from the ocean's surface, it creates an area of low pressure that draws in more air from surrounding areas. The Coriolis effect, that subtle influence of Earth's rotation, causes this inflowing air to spiral, creating the characteristic cyclonic motion. As the storm grows stronger, it develops an eye, a relatively calm centre surrounded by the eye wall, where the most intense winds and precipitation occur. The eye of a hurricane can be 20 to 30 miles across, a strange oasis of calm in the midst of nature's fury. People who have experienced the eye passing over them describe an eerie quiet, with clear skies above and devastation all around, knowing that in a short time, the other side of the storm will arrive with winds from the opposite direction. These great storms are heat engines, converting the thermal energy of warm ocean water into the kinetic energy of wind and the potential energy of lifted water vapor. They can span hundreds of miles and contain more energy than thousands of nuclear weapons, yet they're powered by nothing more than the sun's heat and the ocean's warmth. The winds in these storms don't just blow, they sculpt and reshape everything they touch. They can turn ordinary objects into projectiles, strip leaves from trees, and create storm surges that push ocean water far inland. The storm surge is often the most dangerous aspect of a hurricane, a wall of water that can reach heights of 20 feet or more, flooding coastal areas and causing devastation far from the storm's centre. But weather's drama isn't limited to these grand spectacles. There are also the subtle performers, the phenomena that whisper rather than shout. Fog, for instance, is simply a cloud that forms at ground level, usually when moist air cools to its dew point. It can transform a familiar landscape into something mysterious and dreamlike, muffling sounds and softening edges until the world seems wrapped in grey cotton. Morning dew is another gentle manifestation of weather's artistry. On clear, calm nights, the ground radiates heat into space and cools rapidly. When the air near the ground cools to its dew point, water vapour condenses directly onto grass, leaves and other surfaces, creating those perfect droplets that catch the early morning light like tiny prisms. Frost forms through a similar process, but when the dew point is below freezing, water vapour sublimates directly into ice crystals, creating those delicate, feathery patterns that turn autumn mornings into winter wonderlands. Each frost crystal is a tiny sculpture, created by the invisible artist of temperature and humidity, working together in the still air of dawn. The changing seasons themselves are weather's greatest long-term performance, a slow dance choreographed by the tilt of Earth's axis and our planet's journey around the sun. As Earth orbits the sun, different parts of our planet receive varying amounts of direct sunlight throughout the year. When the northern hemisphere tilts toward the sun, it experiences summer, while the southern hemisphere, tilted away, experiences winter. 6 months later, the situation reverses. This seasonal cycle drives migrations of air masses, the advance and retreat of storm tracks, and the rhythmic expansion and contraction of climate zones. The jet stream, that river of fast-moving air high in the atmosphere, shifts north and south with the seasons, carrying with it the boundaries between warm and cold air masses. In winter, it dips south, bringing Arctic air to regions that might be mild in summer. In summer, it retreats north, allowing tropical warmth to penetrate areas that might be frozen in winter. These seasonal changes create the familiar patterns we associate with different times of year. Spring brings the gradual warming that melts snow and awakens plants from their winter dormancy. The increasing daylight hours and warming temperatures create instability in the atmosphere, leading to the changeable weather and frequent thunderstorms that characterize this season of renewal. Summer brings the intense heating that drives the most dramatic weather events. The long days and high sun angle create strong temperature contrast between day and night, between land and water, between different elevations. This is the season of thunderstorms and hurricanes, of heat waves and droughts, when the atmosphere's energy reaches its peak. Autumn is a time of transition, when the decreasing daylight hours and cooling temperatures begin to stabilize the atmosphere. The great storms of summer give way to gentler, more widespread weather systems. The changing seasons create those crisp, clear days that make autumn such a beloved time of year, when high-pressure systems bring stable weather and the air seems to sparkle with clarity. Winter, in many regions, is weather's quiet season, when the low sun angle and short days reduce the energy available to drive storms. The atmosphere becomes more stable, though it's also the season when the great temperature contrasts between polar and tropical regions create the most intense storm systems. The nor'easters and Alberta clippers that can bring blizzards and ice storms to vast areas. Throughout all these seasonal changes, the ocean plays a crucial moderating role. Water has a remarkable ability to store and release heat, warming and cooling much more slowly than land. This means that coastal areas experience more moderate temperatures than inland regions, with cooler summers and warmer winters. The ocean also provides the moisture that feeds weather systems, evaporating water into the atmosphere that later falls as precipitation hundreds or thousands of miles away. The global circulation of ocean currents creates a vast conveyor belt that transports heat from the equator toward the poles. The Gulf Stream, for instance, carries warm water from the Caribbean north along the eastern coast of North America and then across the Atlantic to Europe. This current helps keep Western Europe much warmer than it would be otherwise. London, despite being at the same latitude as Labrador, enjoys a relatively mild climate thanks to the ocean's warmth. As we drift through this exploration of weather's many moods and manifestations, we begin to understand that what we experience as weather is really the planet's way of redistributing energy, of smoothing out the differences in temperature and pressure that the sun's uneven heating creates. Every cloud that forms, every wind that blows, every storm that rages is part of this vast, ongoing effort to maintain balance in our atmospheric ocean. The air around us is never truly still, never truly at rest. It's constantly moving, constantly changing, responding to the endless interplay of heat and cold, moisture and dryness, pressure and vacuum. We live at the bottom of this atmospheric ocean, feeling its currents as wind on our faces, its condensation as rain on our skin, its temperature as the warmth of summer or the chill of winter. And in this grand theatre of weather, we are both audience and participants. We watch the drama unfold in the sky above us, but we're also part of the story. Our breath adds moisture to the air, our bodies radiate heat that warms the atmosphere around us, and our activities can even influence local weather patterns. Cities, with their concrete and asphalt, create urban heat islands that can trigger thunderstorms. Forests, with their evapotranspiration, can create their own weather systems, generating the moisture that later falls as rain. So, as we continue our gentle journey through the realm of weather, remember that you're not just learning about distant atmospheric processes. You're discovering the intimate connections between yourself and the air that surrounds you, the water that sustains you, and the energy that flows through every moment of your existence. The next time you feel a breeze on your face or watch clouds drift across the sky, you'll understand that you're witnessing the planet's breath, the endless circulation of energy and moisture that makes our world the dynamic, living place it is. Weather's influence extends far beyond the immediate sensations of warmth and cold, wet and dry. It weaves itself into the very fabric of life on Earth, shaping ecosystems, influencing human behavior, and even affecting our moods and health in ways we're only beginning to understand. There's something almost mystical about how the atmosphere's invisible currents can touch the deepest parts of our being, how a change in barometric pressure can make our joints ache, or how the approach of a storm can leave us feeling restless and unsettled. Animals have always been more sensitive to these atmospheric changes than we are. Birds can sense shifts in air pressure that signal approaching storms, often altering their migration patterns or seeking shelter hours before the first clouds appear. Dogs and cats become restless before thunderstorms, pacing and whimpering as they feel the electrical charges building in the air. Even insects respond to weather changes, with ants working more frantically to secure their colonies when they sense rain approaching, and bees returning to their hives when the barometric pressure drops. This sensitivity to weather isn't just instinct, it's survival. For millions of years, life on Earth has evolved in intimate relationship with the atmosphere's moods. Plants open and close their stomata, the tiny pores in their leaves, in response to humidity levels. Trees can sense approaching drought through subtle changes in atmospheric moisture and begin conserving water by shedding leaves or entering dormancy. Flowers track the sun's movement across the sky, following its warmth and light like devoted dancers. Human beings, despite our modern insulation from the elements, still carry these ancient sensitivities within us. Many people report feeling more energetic on clear, high-pressure days and more lethargic when storm systems approach. There's actually a scientific basis for this. Changes in atmospheric pressure can affect the amount of oxygen in our bloodstream, while shifts in humidity can influence our body's ability to regulate temperature. Some individuals are so sensitive to these changes that they can predict weather more accurately than meteorologists, their bodies serving as living barometers. The phenomenon of seasonal affective disorder reminds us how profoundly weather and light can influence our mental state. During the shorter days of winter, when sunlight becomes scarce, some people experience depression and lethargy. Their bodies miss the bright light that helps regulate our circadian rhythms and the production of important neurotransmitters. It's as if our souls are designed to dance with the sun, and when that cosmic partner withdraws, we feel the absence in our very bones. But weather's influence on human life goes far beyond individual health and mood. It has shaped the entire course of human civilization, determining where we built our cities, how we grew our food, and even how we developed our cultures. The monsoon rains that sweep across South Asia each summer have dictated the rhythm of life for billions of people for thousands of years. Farmers plant their crops in anticipation of these seasonal rains, knowing that their success or failure depends on the atmosphere's punctuality. The trade winds that blow steadily across the tropical oceans enable the age of sail, connecting distant continents and allowing the exchange of goods, ideas, and cultures. These reliable winds, created by the temperature differences between land and sea, became the highways of early globalization. Sailors learned to read the sky like a book, understanding that certain cloud formations meant steady winds, while others warned of dangerous storms. Even our architecture reflects our relationship with weather. The steep roofs of northern European houses are designed to shed snow quickly, while the flat roofs of desert dwellings help keep interiors cool. The large windows and porches of tropical homes encourage air circulation, while the small windows and thick walls of Arctic buildings conserve heat. Every culture has developed its own solutions to the challenges and opportunities that weather presents. Weather has also been a source of inspiration for art, literature, and music throughout human history. Poets have found metaphors in storms and sunshine, painters have captured the ever-changing moods of the sky, and composers have written symphonies that echo the rhythms of rain and wind. There's something about weather's constant change, its blend of beauty and power, that speaks to the human spirit. Perhaps it's because weather, like our own emotions, is always in motion, always transitioning from one state to another. The science of meteorology itself is a relatively recent development in human history. For most of our existence, weather prediction was based on observation, folklore, and intuition. Farmers watched the behavior of animals and the appearance of clouds to predict the next day's weather. Sailors learned to read the wind and waves to avoid dangerous storms. This traditional knowledge, passed down through generations, was surprisingly accurate within its limited scope. The development of scientific weather prediction began in earnest during the 19th century, when the telegraph allowed weather observations to be shared quickly across large distances. For the first time, meteorologists could see the big picture, tracking storm systems as they moved across continents. This was the beginning of modern weather forecasting, though it remained as much art as science for many decades. The real revolution in weather prediction came with the development of computers and satellites in the 20th century. Suddenly, meteorologists could process vast amounts of data and run complex mathematical models that simulated the behavior of the atmosphere. Satellites provided a god's-eye view of weather systems, showing their structure and movement in unprecedented detail. Today's weather forecasts, while still not perfect, are remarkably accurate compared to the educated guesses of earlier generations. These technological advances have also revealed the incredible complexity of the atmosphere. Weather systems that once seemed chaotic and unpredictable are now understood to follow physical laws, though those laws operate in systems so complex that small changes can have enormous consequences. This is the essence of chaos theory, the mathematical understanding that tiny variations in initial conditions can lead to vastly different outcomes. The butterfly effect, that poetic notion that a butterfly flapping its wings in Brazil could trigger a tornado in Texas, captures this atmospheric sensitivity perfectly. While an actual butterfly probably can't cause a tornado, the principle holds true. Small disturbances in the atmosphere can indeed grow into major weather events, given the right conditions. This is why weather forecasting remains challenging beyond a week or so. The atmosphere's sensitivity to initial conditions means that small errors in measurement or modelling can compound rapidly. Climate change has added new urgency to our understanding of weather systems. As greenhouse gases trap more heat in the atmosphere, the engine that drives weather is becoming more powerful. Warmer air can hold more moisture, leading to more intense precipitation events. Higher sea surface temperatures provide more energy for hurricanes and typhoons. The jet stream, that river of fast-moving air that steers weather systems, is becoming more erratic as the temperature difference between the poles and equator decreases. These changes mean that the weather patterns our ancestors knew, the seasonal rhythms that shaped human civilization, are shifting. Spring is arriving earlier in many regions, while winter is becoming shorter and less severe. Extreme weather events are becoming more frequent and intense. Droughts are lasting longer, while floods are becoming more devastating. The atmosphere is writing a new chapter in Earth's story, and we're all living through this historic transition. Yet for all our scientific understanding, weather retains its capacity to surprise and humble us. Despite our satellites and supercomputers, despite our sophisticated models and global observation networks, the atmosphere still keeps some of its secrets. Every meteorologist has stories of forecasts that went wrong, of storms that appeared out of nowhere or dissipated unexpectedly. The atmosphere is simply too complex, too sensitive, too vast for us to predict with complete accuracy. This unpredictability is part of weather's enduring fascination. Each day brings new possibilities, new combinations of temperature, pressure, and moisture that create unique atmospheric conditions. No two sunsets are exactly alike. No two snowflakes are identical. No two storms follow precisely the same path. Weather is nature's improvisation, a constant creative performance played out on the stage of the sky. The water cycle, that endless circulation of moisture between ocean, atmosphere, and land, is perhaps the most beautiful example of weather's interconnectedness. Every drop of water in the clouds above your head has been on an incredible journey. It may have fallen as rain in a distant forest, flowed through rivers to the sea, evaporated under tropical sunshine, and been carried thousands of miles by wind currents before condensing into the clouds you see today. This same water has been cycling through the atmosphere for billions of years, falling as rain on ancient seas, being absorbed by primordial forests, and eventually returning to the sky to begin the journey again. The water in your body, the water you drink, the water that nourishes the plants around you, all of it is part of this vast atmospheric circulation. We are all connected through this invisible web of moisture, all participants in the planet's great water dance. Ocean currents play a crucial role in this global circulation, acting as vast conveyor belts that transport heat and moisture around the planet. The Gulf Stream, that mighty river of warm water that flows north along the eastern coast of North America, carries more than 100 times the flow of all the world's rivers combined. This current helps moderate temperatures across the North Atlantic, keeping Western Europe much warmer than it would be otherwise. When these ocean currents shift or weaken, the effects can be felt across entire continents. The El Niño and La Niña phenomena, those periodic changes in Pacific Ocean temperatures, can alter weather patterns globally. During El Niño years, the eastern Pacific becomes unusually warm, disrupting normal wind patterns and bringing drought to some regions while causing floods in others. La Niña, the opposite phase, tends to enhance normal patterns, often leading to more active hurricane seasons and cooler temperatures. These global climate oscillations remind us that weather is not just local, but planetary. The atmosphere doesn't recognize political boundaries or geographical divisions. A volcanic eruption in one part of the world can affect weather patterns globally by injecting particles into the atmosphere that reflect sunlight back to space. The dust storms of the Sahara Desert provide nutrients to the rainforests of the Amazon, carrying minerals across thousands of miles of ocean. The atmosphere is truly a global commons, shared by all life on Earth. As we float deeper into our understanding of weather's grand design, we begin to see patterns within patterns, cycles within cycles. There are the daily rhythms of heating and cooling, the seasonal cycles of Earth's orbit around the Sun, and the longer-term oscillations that operate on scales of years or decades. The atmosphere is like a vast musical composition, with melodies and harmonies playing out across multiple timescales. The diurnal cycle, that daily rhythm of temperature change, creates its own weather patterns. During the day, the sun heats the ground, which in turn heats the air above it. This creates thermals, columns of rising warm air that can trigger the formation of cumulus clouds. By afternoon, these clouds may have grown into thunderstorms, especially during the summer months when the heating is most intense. As evening approaches and the sun sets, the atmosphere begins to cool and stabilize, and the storms typically weaken and dissipate. Mountain regions create their own special weather patterns through this daily heating cycle. During the day, the slopes facing the sun heat up more quickly than the surrounding valleys, creating upslope winds as the warm air rises. These winds can trigger afternoon thunderstorms over the peaks. At night, the process reverses. The mountain slopes cool rapidly, creating downslope winds that flow like invisible rivers of cold air into the valleys below. Coastal areas experience similar daily wind patterns. During the day, the land heats up faster than the ocean, creating a pressure difference that draws cool ocean air inland. This is the sea breeze that provides relief from hot summer days in coastal cities. At night, the land cools faster than the ocean, reversing the pressure gradient and creating a land breeze that flows from shore to sea. These local wind patterns are like the atmosphere's way of evening out temperature differences on a small scale, just as the global circulation patterns work to balance temperatures on a planetary scale. The atmosphere is constantly seeking equilibrium, constantly working to smooth out the wrinkles that the sun's uneven heating creates. But the atmosphere's quest for balance is never quite achieved, and that's what keeps weather interesting. If the atmosphere ever reached perfect equilibrium, if temperatures and pressures were perfectly uniform everywhere, weather would cease to exist. The sky would be clear and still with no wind, no clouds, no storms. It would be peaceful perhaps, but also lifeless and monotonous. The very instability that creates weather's drama is also what makes Earth a dynamic, living planet. The beauty of weather lies not just in its grand spectacles, but in its subtle details. The way morning mist rises from a lake like the breath of sleeping water. The gentle spiral of leaves caught in a dust devil. The perfect hexagonal symmetry of snowflakes. The rainbow that appears when sunlight meets raindrops at just the right angle. These small miracles happen around us every day, reminders that the atmosphere is not just a scientific system, but a source of wonder and beauty. Even the simplest weather phenomena involve complex physics. A rainbow, for instance, is created when sunlight enters water droplets in the air, is refracted and reflected inside the droplets, and then exits at a specific angle. The different colours of light are bent by different amounts, creating the spectrum we see. The secondary rainbow, fainter and with colours reversed, is created by light that reflects twice inside the water droplets before exiting. Frost patterns on windows are another example of weather's artistry. These delicate, fern-like designs form when water vapour in the air comes into contact with a surface that's below the freezing point. The water vapour sublimates directly into ice crystals, and the patterns they create depend on tiny variations in temperature and humidity across the surface. No two frost patterns are exactly alike, each one a unique creation of the invisible forces at work in the atmosphere. The northern and southern lights, those ethereal curtains of colour that dance across polar skies, are weather phenomena of sorts, though they occur much higher in the atmosphere than typical weather. These auroras are created when charged particles from the sun interact with Earth's magnetic field and atmosphere, causing gases in the upper atmosphere to glow. While not weather in the traditional sense, they remind us that Earth's atmosphere extends far beyond the troposphere where our daily weather occurs. As we near the end of our gentle journey through weather's realm, we find ourselves with a deeper appreciation for the invisible ocean that surrounds us. Weather is not just something that happens to us, it's something we live, within, something that shapes our daily lives in countless ways, from the air we breathe to the clothes we wear, from the food we eat to the activities we choose. Weather influences nearly every aspect of human existence. The next time you step outside, take a moment to feel the air against your skin. Notice its temperature, its humidity, its movement. Listen to the sounds it carries, the rustle of leaves, the distant rumble of thunder, the gentle sigh of wind through grass. Look up at the sky and see the stories written in the clouds, the promises of sunshine or threats of storms. You're swimming in an ocean of air, breathing the same atmosphere that has nurtured life on Earth for billions of years. Weather connects us all, from the farmer checking the sky for signs of rain, to the pilot navigating through clouds, from the child making snow angels to the meteorologist tracking hurricanes. We all share this atmospheric commons, this invisible realm where water vapor dances with air currents, where temperature and pressure create the endless variety of conditions we call weather. And in this shared experience of weather, we find something profound about our place in the universe. We are not separate from nature, but part of it, breathing its breath, warmed by its sun, cooled by its breezes. Weather reminds us that we live on a planet that is alive, dynamic, and ever-changing. It teaches us about the delicate balance that sustains life, the interconnectedness of all things, and the beauty that can emerge from the complex dance of natural forces. So, as you settle into sleep tonight, listening perhaps to the gentle patter of rain or the whisper of wind through trees, remember that you are part of this grand atmospheric story. Your breath mingles with the air around you, your body radiates warmth into the night, and your dreams float on the same currents that carry clouds across the sky. Weather is not just around you, but within you, connecting you to the endless circulation of energy and moisture that makes our world the beautiful, dynamic place it is. In this gentle realm of atmospheric wonder, we discover that weather possesses its own memory, its own way of recording the stories of our planet's past and whispering hints about its future. Tree rings tell tales of wet years and dry years, their width revealing the weather patterns that shaped their growth decades or even centuries ago. Ice cores drilled from ancient glaciers hold tiny bubbles of atmosphere, trapped from long ago, preserving samples of the air our ancestors breathed and the climate conditions that surrounded them. These natural archives reveal that Earth's weather has always been in flux, always changing, always writing new chapters in the story of our planet. There have been ice ages when glaciers covered much of North America and Europe, and there have been warm periods when palm trees grew in what is now Alaska. The atmosphere has danced through countless variations, each one shaping the evolution of life in profound ways. Coral reefs, too, serve as living libraries of climate history. The calcium carbonate they lay down each year contains chemical signatures that reflect the temperature and chemistry of the ocean waters in which they grew. Scientists can read these coral records like pages in a book, discovering how tropical weather patterns have shifted over centuries and millennia. The study of these natural climate records, called paleoclimatology, reveals that our current understanding of weather represents just a tiny slice of atmospheric history. The weather patterns we consider normal, the seasonal rhythms we've grown accustomed to, are really just one brief movement in a much longer symphony. Earth's climate system operates on timescales that dwarf human experience, with cycles that unfold over thousands, millions, even hundreds of millions of years. Solar cycles, those periodic changes in the sun's energy output, influence Earth's climate on scales of decades. The sun's magnetic field strengthens and weakens in roughly 11-year cycles, affecting the number of sunspots and the amount of energy reaching Earth. During periods of low solar activity, Earth tends to cool slightly, while periods of high activity bring a bit more warmth. These variations are subtle, but they can nudge weather patterns in directions that accumulate over time. Volcanic eruptions provide dramatic punctuation marks in the climate record. When a major volcano explodes, it can inject millions of tons of sulfur dioxide into the stratosphere, where it forms tiny particles that reflect sunlight back to space. The result is often a temporary cooling that can last for several years. The eruption of Mount Tambora in 1815 created such significant cooling that the following year became known as the Year Without a Summer, with crop failures and unusual weather patterns across the globe. These natural climate variations remind us that weather and climate exist within a much larger context than our daily experience suggests. The atmosphere is part of a complex system that includes the oceans, the ice sheets, the land surface, and even the movements of continents over geological time. All of these components interact with each other in ways that can amplify or dampen changes, creating feedback loops that can stabilize the climate or push it toward new states. The ocean's role in this grand system cannot be overstated. The seas cover more than 70% of Earth's surface and contain about 50 times more carbon dioxide than the atmosphere. Ocean currents transport enormous amounts of heat around the planet, and the ocean's ability to absorb and release gases affects the composition of the atmosphere itself. When the ocean warms, it releases more water vapor into the atmosphere, and water vapor is itself a greenhouse gas that can trap heat and cause further warming. Ice sheets and glaciers act as the planet's air conditioning system, reflecting sunlight back to space and helping to keep temperatures cool. But when ice melts, it exposes darker surfaces underneath, which absorb more heat and can accelerate the melting process. This is one of those feedback loops that can cause relatively small changes to grow into much larger ones over time. Forests and grasslands also play crucial roles in the climate system. Plants absorb carbon dioxide from the atmosphere during photosynthesis, helping to regulate the concentration of this important greenhouse gas. But the relationship between vegetation and climate is complex and two-way. Climate affects where plants can grow and how well they thrive, while plants affect local and regional weather patterns through their influence on humidity, temperature, and wind patterns. The Amazon rainforest, for instance, creates much of its own rainfall through the process of evapotranspiration. The trees release water vapor into the atmosphere, which later condenses and falls as rain, often within the forest itself. This creates a recycling system where the forest essentially irrigates itself. When parts of the forest are cleared, this recycling system is disrupted, potentially leading to drier conditions that make it harder for the remaining forest to survive. Urban areas create their own unique weather patterns through what meteorologists call the urban heat island effect. Cities tend to be warmer than the surrounding countryside because concrete and asphalt absorb and retain heat more effectively than natural surfaces. This temperature difference can trigger thunderstorms, alter wind patterns, and even affect precipitation. Some cities are warm enough to create their own weather systems, with air rising over the hot urban core and drawing in cooler air from the surrounding areas. The study of urban meteorology has become increasingly important as more of the world's population moves to cities. Understanding how buildings, streets, and human activities affect local weather patterns helps urban planners design cities that are more comfortable and energy efficient. Green roofs, urban forests, and water features can all help moderate the urban heat island effect and create more pleasant microclimates within cities. Agriculture, too, has a complex relationship with weather. Farmers have always been weather watchers, timing their planting and harvesting to match seasonal patterns. But modern agriculture also influences weather patterns through irrigation, which adds moisture to the atmosphere, and through land use changes that can affect local temperatures and wind patterns. Large-scale irrigation can even create clouds and precipitation downwind of agricultural areas. The relationship between human activities and weather patterns has become one of the most important scientific questions of our time. While natural climate variations continue to operate, human influences on the atmosphere are now significant enough to affect global weather patterns. The burning of fossil fuels has increased the concentration of carbon dioxide in the atmosphere to levels not seen for millions of years, and this is altering the energy balance that drives all weather systems. Climate models, those sophisticated computer simulations that attempt to predict future weather patterns, suggest that we're entering a period of more extreme weather. Not necessarily more storms or higher temperatures everywhere, but more variability, more extremes, more frequent departures from the patterns our grandparents knew. Heat waves may become hotter and last longer. Droughts may become more severe in some regions, while others experience more intense precipitation. The jet stream, that river of fast-moving air that steers weather systems, may become more erratic as the temperature difference between the poles and equator changes. These projections remind us that weather is not just a backdrop to human life, but an active participant in our future. The choices we make about energy, transportation, land use, and consumption all influence the atmospheric conditions that will shape weather patterns for generations to come. We are not just observers of weather, but participants in its creation. Yet for all our growing influence on atmospheric conditions, weather retains its fundamental character as a natural force beyond our direct control. We can influence climate trends over decades and centuries, but we cannot command tomorrow's weather. The atmosphere continues to follow physical laws that operate independently of human desires or intentions. A hurricane doesn't care about our vacation plans, and a drought doesn't pause for economic considerations. This tension between human influence and natural variability creates both challenges and opportunities. Understanding weather patterns becomes more important as those patterns change, but also more difficult as the historical records we rely on become less reliable guides to future conditions. Weather forecasting, already a complex challenge, becomes even more demanding when the basic patterns are shifting. The science of weather modification, the attempt to deliberately alter weather patterns, has intrigued researchers for decades. Cloud seeding, the practice of introducing particles into clouds to encourage precipitation, has shown some success in increasing rainfall or reducing hail damage. But the results are often modest and difficult to verify, and the unintended consequences of weather modification remain poorly understood. The atmosphere is so complex and interconnected that changing one thing often affects many others in unpredictable ways. Perhaps the most profound lesson from our journey through weather's realm is the recognition of our fundamental dependence on atmospheric conditions. Every breath we take, every sip of water we drink, every bite of food we eat depends on the proper functioning of weather systems. The oxygen we breathe is maintained at stable levels by the circulation of the atmosphere. The fresh water we depend on is delivered by precipitation and stored in rivers, lakes, and groundwater. The crops that feed us grow in soil enriched by rainfall and warmed by sunshine. This dependence extends to nearly every aspect of modern life. The electricity that powers our homes often comes from wind turbines that harvest atmospheric motion or solar panels that capture the sun's energy filtered through the atmosphere. The transportation systems that connect our communities must account for weather conditions, from the roads that ice over in winter to the airports that close during storms. Even our indoor environments depend on weather, as heating and cooling systems work to maintain comfortable conditions regardless of what's happening outside. Weather also shapes our cultural expressions and emotional lives in ways both obvious and subtle. The paintings of the Impressionists captured the changing light and atmosphere of different times of day and seasons. Musical compositions have long drawn inspiration from the sounds and rhythms of weather, from Vivaldi's Four Seasons to the countless folk songs that celebrate or lament particular weather conditions. Poetry and literature are filled with weather metaphors, using atmospheric conditions to express human emotions and experiences. The emotional impact of weather is more than just metaphorical. Bright sunny days tend to lift our spirits, while grey, overcast conditions can make us feel gloomy. This isn't just imagination. Research has shown that exposure to natural light affects the production of neurotransmitters in our brains. The changing seasons can trigger profound emotional responses, from the joy of spring's first warm day to the melancholy that sometimes accompanies autumn's shorter days. Weather also influences our social behaviour in interesting ways. Pleasant weather encourages outdoor activities and social gatherings, while severe weather drives us indoors and can create shared experiences of survival and recovery. Some of the strongest community bonds are forged during weather emergencies, when neighbours help each other through storms, floods, or other atmospheric challenges. The rhythm of seasons has always provided structure to human societies. Traditional cultures developed festivals and ceremonies that marked important seasonal transitions, celebrating the return of spring rains or the harvest of autumn crops. Modern societies may be less directly dependent on seasonal weather patterns, but we still organise much of our social life around these natural rhythms, from school years that begin in autumn to vacation seasons that coincide with summer weather. Children seem to have an especially intimate relationship with weather. They notice changes in atmospheric conditions that adults might miss, and they often respond with pure joy to phenomena like falling snow or summer thunderstorms. Perhaps this is because children are more present in their bodies, more attuned to sensory experiences, less distracted by the abstract concerns that occupy adult minds. Watching a child experience their first snowfall or run through a spring rain shower reminds us of weather's capacity to inspire wonder and delight. Weather also teaches us important lessons about acceptance and adaptation. Unlike many other aspects of our environment, weather cannot be controlled through human effort or technology. We can predict it with increasing accuracy, prepare for it with better planning, and protect ourselves with improved infrastructure. But ultimately, we must accept what the atmosphere delivers. This acceptance can be a source of wisdom, reminding us that some forces in life are beyond our control, and that our happiness and well-being depend partly on our ability to adapt to changing conditions. The unpredictability of weather also serves as a metaphor for life's uncertainties. Just as we cannot know with complete certainty what tomorrow's weather will bring, we cannot predict all the challenges and opportunities that lie ahead in our personal lives. Weather teaches us to be prepared for various possibilities while remaining open to surprise and change. Seasonal changes offer lessons about the natural rhythms of growth, rest, and renewal. Spring reminds us that new beginnings are always possible, that life has an irrepressible tendency to emerge and flourish. Summer teaches us about abundance and energy, about making the most of favourable conditions. Autumn shows us the beauty that can be found in letting go, in the graceful release of what has served its purpose. Winter demonstrates the value of rest and reflection, the necessity of dormant periods that prepare us for future growth. The study of weather also reveals important principles about complex systems and interconnectedness. The atmosphere shows us how small changes can have large consequences, how local events can influence distant regions, and how multiple factors interact in ways that create emergent properties. These insights from meteorology have applications far beyond weather prediction, influencing fields from economics to ecology to social science. Weather forecasting itself is a remarkable human achievement that demonstrates our capacity to understand complex natural systems. The fact that we can predict with reasonable accuracy what atmospheric conditions will be like several days in advance represents centuries of scientific progress, from the development of instruments to measure temperature and pressure to the creation of mathematical models that can simulate atmospheric behaviour. Modern weather prediction relies on a global network of observations, from surface weather stations to radio sondes that measure conditions high in the atmosphere, from satellites that provide a global view to radar systems that track precipitation and wind patterns. This international cooperation in weather observation and forecasting shows how scientific collaboration can transcend political boundaries in service of shared human needs. The data collected by this global observation network creates a continuous real-time portrait of Earth's atmospheric state. Every 6 hours, weather services around the world feed their observations into sophisticated computer models that simulate how atmospheric conditions will evolve over the coming days. These models solve mathematical equations that represent the fundamental physics of atmospheric motion, heat transfer, and moisture transport. Yet despite all this technology and scientific understanding, weather forecasting remains as much art as science. Meteorologists must interpret model output, recognize patterns, and apply their experience to situations that may not have exact precedents. The best forecasters combine scientific knowledge with intuition, statistical analysis with pattern recognition, global perspective with local expertise. The limitations of weather prediction remind us of the fundamental complexity of natural systems. The atmosphere is what mathematicians call a chaotic system, one where small differences in initial conditions can lead to vastly different outcomes. This doesn't mean atmospheric behavior is random, but it does mean that precise long-term prediction is impossible, even in principle. There will always be an element of uncertainty in weather forecasting, a reminder that nature retains some of its mystery despite our best efforts to understand it. This uncertainty is not a failure of science, but a feature of reality. The atmosphere's sensitivity to initial conditions is part of what makes weather interesting and dynamic. If atmospheric behavior were completely predictable, if we could forecast weather months or years in advance with perfect accuracy, the atmosphere would be a much simpler and less fascinating system. The element of surprise in weather keeps us engaged with our environment, keeps us paying attention to the sky and the wind and the changing seasons. As we float toward the end of our exploration, we find ourselves with a deeper appreciation for the magnificent complexity of the atmospheric system that surrounds us. Weather is simultaneously a global phenomenon and an intimate personal experience, a manifestation of universal physical laws and a source of endless local variation. It connects us to the planet's deepest rhythms, while surprising us with daily novelties. The invisible ocean of air that we swim through every day is far more than empty space between objects. It's a dynamic medium that carries energy, moisture, and life itself. It's a communication system that brings us the scents of distant flowers and the sounds of far-off thunder. It's a transportation network that moves seeds and pollen, birds and butterflies, clouds and storms across vast distances. Every breath you take connects you to this vast atmospheric circulation, making you a participant in the planet's respiratory system. The oxygen that sustains your life was created by plants through photosynthesis, released into the atmosphere, and circulated by winds and weather patterns before reaching your lungs. The carbon dioxide you exhale will become part of the atmospheric mix, eventually being absorbed by plants or dissolved in the ocean, continuing the endless cycle of atmospheric chemistry. Weather reminds us that we live not on a static world, but on a dynamic planet where everything is connected to everything else. The rain that falls on your garden may have evaporated from tropical seas thousands of miles away. The wind that rustles through your hair may have begun as a temperature difference between land and ocean on a distant continent. The clouds that drift past your window are temporary sculptures in an ever-changing gallery of sky art. Understanding weather helps us understand our place in the natural world. We are not separate from the atmospheric system, but embedded within it, shaped by it, and increasingly influential upon it. The choices we make about how we live, what we consume, and how we treat the environment all contribute to the atmospheric conditions that will determine future weather patterns. Weather also teaches us about the beauty that emerges from complexity, the intricate patterns of frost on a window, the majestic spiral of a hurricane seen from space, the delicate architecture of a snowflake, the brilliant colours of a sunset. All these manifestations of beauty arise from the interaction of simple physical laws operating in complex systems. The atmosphere is nature's art studio, constantly creating new masterpieces from the basic materials of air, water, and energy. As you prepare for sleep tonight, perhaps you can hear the gentle sounds of weather outside your window. Maybe it's the whisper of wind through leaves, the distant rumble of thunder, the soft patter of rain, or simply the profound silence of still air. These sounds are the voice of the atmosphere, the audible expression of invisible forces at work in the ocean of air that surrounds us. When you wake tomorrow morning, you'll step into a slightly different atmospheric world than the one you left behind tonight. The air will have moved, the moisture will have redistributed, the pressure will have shifted, and somewhere new clouds will be forming while others dissolve. Weather never sleeps, never pauses, never repeats itself exactly. It's always creating something new, always in motion, always changing. And in this constant change, this endless variety, this beautiful unpredictability, we find one of nature's most profound gifts. Weather keeps the world interesting, keeps us connected to natural rhythms, keeps us humble before forces greater than ourselves. It reminds us that we are part of something vast and magnificent, participants in a planetary system that has been operating for billions of years and will continue long after we're gone. So rest well tonight, knowing that you're held safely within this atmospheric embrace, this invisible ocean that connects you to every other living thing on Earth. Let the gentle sounds of weather lull you toward dreams, and when you wake, step outside with new eyes to see the miraculous ordinary magic of the air that surrounds us all. Perhaps there's no phenomenon quite as mesmerizing as watching the dance between air masses when they meet along what meteorologists call frontal boundaries. These invisible lines in the sky mark where different worlds of air collide, where the atmosphere writes some of its most dramatic stories. Picture warm, moist air from the tropics, meeting cool, dry air from the polar regions. They don't blend gently like cream stirred into coffee. Instead, they maintain their distinct identities, creating boundaries that can stretch for hundreds of miles and trigger some of the most spectacular weather events on our planet. A cold front is like nature's bulldozer, pushing underneath the warmer air ahead of it with determined force. The cold air, being denser and heavier, slides beneath the warm air like a wedge, forcing it rapidly upward. This sudden lifting creates towering cumulus clouds that can explode into thunderstorms within hours. The leading edge of a cold front often brings a dramatic line of storms, complete with lightning, heavy rain, and sometimes even tornadoes. Behind the front, the air clears quickly, leaving behind crisp, cool conditions and brilliant blue skies that seem to sparkle with clarity. Warm fronts, by contrast, are the gentle giants of the atmospheric world. They approach like slow-moving tides, gradually overriding the cooler air ahead of them. The warm air slides up and over the cold air mass in a gradual slope that can extend for hundreds of miles. This creates layered clouds that arrive in a predictable sequence. First, the high, wispy cirrus clouds that appear like brushstrokes against the sky. Then the thickening altostratus that creates a milky veil over the sun. And finally, the low, grey nimbostratus clouds that bring steady, soaking rain. The passage of fronts creates some of the most noticeable changes in our daily weather. You might wake up to warm, humid air and find yourself reaching for a sweater by evening as a cold front moves through. The barometric pressure drops as the front approaches, often causing that restless feeling that both humans and animals experience before storms. Then, as the front passes, the pressure rises sharply, the wind shifts direction, and the temperature can drop 10 or 20 degrees in just a few hours. These frontal systems are like travelling theatres, carrying their own cast of weather characters from place to place. A storm system that brings snow to the Rocky Mountains might transform into severe thunderstorms on the Great Plains, then weaken into gentle rain showers by the time it reaches the Atlantic coast. The same atmospheric energy, the same basic ingredients of temperature and moisture create entirely different performances depending on the local terrain and conditions they encounter. Mountains play a particularly fascinating role in shaping weather patterns. When air masses encounter mountain ranges, they're forced to rise, and this lifting often triggers dramatic weather changes. The windward side of mountains, where the air is forced upward, typically receives much more precipitation than the leeward side. This creates what meteorologists call a rain shadow effect, where one side of a mountain range might be lush and green while the other side is arid and desert-like. The Sierra Nevada mountains in California provide a perfect example of this phenomenon. Moist air from the Pacific Ocean rises up the western slopes, cooling and dropping its moisture as snow and rain. By the time the air crosses the peaks and descends into Nevada, it has lost most of its moisture, creating the dry conditions that characterize much of the Great Basin. This same process operates on smaller scales too. Even modest hills can create their own microclimates, with one valley experiencing frequent fog while the next valley over remains clear. Altitude itself creates its own weather world. For every 1,000 feet you climb, the temperature typically drops about 3.5 degrees Fahrenheit. This is why mountain peaks can be snow-covered, even when the valleys below are experiencing spring warmth. The thin air at high altitudes also holds less moisture, which is why mountain air often feels so crisp and clear. Breathing becomes more difficult not just because there's less oxygen, but because the air pressure is lower, making each breath less satisfying. The jet stream, that river of fast-moving air high in the atmosphere, acts like a steering wheel for weather systems. These high-altitude winds, which can reach speeds of over 200 miles per hour, guide storm systems along their paths and determine where weather patterns will develop. When the jet stream takes a wavy pattern, it can bring Arctic air far to the south or allow tropical warmth to penetrate unusually far north. The position and strength of the jet stream can determine whether a region experiences a harsh winter or a mild one, a wet season or a dry spell. Meteorologists have learned to read the jet stream like a roadmap, using it to predict where storms will travel and how intense they might become. Satellites now allow us to see these high-altitude wind patterns in remarkable detail, revealing the invisible highways that guide our weather. The jet stream's behavior is influenced by the temperature difference between polar and tropical regions, and as this difference changes with the seasons and longer-term climate patterns, the jet stream's path shifts accordingly. The ocean's influence on weather extends far beyond simply providing moisture for the atmosphere. The thermal mass of water means that oceans heat up and cool down much more slowly than land, creating temperature contrasts that drive weather patterns. Coastal areas benefit from this moderating influence, rarely experiencing the extreme temperatures that continental interiors face. The ocean also stores enormous amounts of heat energy, which can be released to fuel powerful storm systems. Sea surface temperatures are like the fuel gauge for hurricanes and typhoons. These massive storms can only form and maintain their strength over water that's at least 80 degrees Fahrenheit. As they move over cooler water or make landfall, they begin to weaken, their energy source cut off. This is why hurricanes often lose intensity as they move north into cooler waters, though they can still bring destructive winds and flooding to areas far from the tropics. The daily heating and cooling cycle creates its own rhythm of atmospheric activity. During the day, the sun's energy heats the ground, which in turn heats the air above it. This creates instability as warm air rises and cooler air sinks, often leading to the formation of cumulus clouds and afternoon thunderstorms. As evening approaches and the sun's angle becomes lower, the heating weakens and the atmosphere tends to stabilize. This is why thunderstorms often develop in the afternoon and evening, then weaken or dissipate overnight. Night brings its own subtle weather phenomena. As the ground radiates heat into space and cools, the air near the surface becomes cooler and denser. This can create temperature inversions, where the air near the ground is actually cooler than the air above it. These inversions can trap moisture near the surface, leading to the formation of dew, frost, or fog. They can also trap pollutants, which is why air quality is often worse on calm, clear nights when inversions form. Valley fog is a beautiful example of how local topography interacts with these nightly cooling processes. Cold air, being denser than warm air, flows downhill like an invisible river, pooling in valleys and low-lying areas. When this cold air is moist enough, it can create fog that fills valleys like a white sea, leaving hilltops poking up like islands. Driving through valley fog can be like descending into a cloud, with visibility dropping to just a few feet. Radiation fog forms through a similar process, but on flatter terrain. On clear, calm nights, the ground loses heat rapidly through radiation to space. This cools the air near the surface to its dew point, creating fog that can persist well into the morning until the sun's warmth burns it off. These fog patterns follow predictable cycles, often forming in the same locations night after night when conditions are right. The boundary layer, that lowest part of the atmosphere where we live and breathe, has its own complex dynamics that create the weather we experience most directly. This layer, typically extending from the ground up to about 3,000 feet, is where the atmosphere interacts most directly with the Earth's surface. Here, friction from trees, buildings, and terrain slows down the wind and creates turbulence. Heat from pavement and buildings creates updrafts, while cool air from parks and water bodies creates downdrafts. Urban heat islands demonstrate how human activities can create their own weather patterns. Cities, with their concentration of concrete, asphalt, and heat-generating activities, can be several degrees warmer than the surrounding countryside. This temperature difference can trigger thunderstorms, alter wind patterns, and even affect precipitation. Some cities are large enough and warm enough to create their own circulation patterns, with air rising over the hot urban core and drawing in cooler air from the suburbs. The study of these urban weather patterns has become increasingly important as more of the world's population moves to cities. Understanding how buildings and streets affect local airflow helps architects and urban planners design cities that are more comfortable and energy efficient. The placement of parks, the orientation of buildings, and even the colour of roofing materials can all influence local weather conditions. Microclimates exist everywhere, creating pockets of different weather conditions within short distances. The south side of a building might be significantly warmer than the north side. A garden sheltered by trees might have different humidity and temperature than an open lawn just a few yards away. Bodies of water create their own microclimates, moderating temperatures and increasing humidity in their immediate vicinity. These small-scale weather variations remind us that the atmosphere is not uniform but infinitely varied, creating unique conditions in every location. A meteorologist might forecast partly cloudy skies with temperatures in the 70s, but your specific location might experience something quite different depending on local factors like elevation, proximity to water, urban development, and terrain features. Agricultural meteorology recognizes these local variations and their importance for farming. Farmers have always been keen observers of microclimates, knowing that frost might settle in low-lying fields while higher ground remains clear, or that one side of a hill might receive enough moisture while the other side struggles with drought. Modern precision agriculture uses detailed weather monitoring to optimize planting, irrigation, and harvesting decisions based on very localized conditions. The relationship between weather and plant life extends beyond simple cause and effect. Plants don't just respond to weather, they also influence it through processes like transpiration, the release of water vapor through their leaves. A large forest can add significant moisture to the atmosphere, affecting humidity and even precipitation patterns downwind. The Amazon rainforest is estimated to recycle about half of its own rainfall through this process, creating a self-sustaining weather system. Seasonal changes in vegetation create their own weather effects. In spring, as leaves emerge and plants begin actively growing, they start pumping moisture into the atmosphere. This can increase humidity and contribute to the unstable atmospheric conditions that often make spring such an active weather season. In autumn, as plants prepare for winter dormancy, they reduce their moisture output, contributing to the drier, more stable conditions that characterize fall weather in many regions. Weather folklore, passed down through generations of careful observers, often contains surprising accuracy. Sayings like "red sky at night, sailors delight, red sky at morning, sailors take warning," actually have meteorological basis. A red sunset often indicates high pressure and clear weather to the west, suggesting fair weather ahead. A red sunrise can indicate moisture and possible storm systems approaching from the west. Animals, too, have long been recognized as weather predictors. Their behavior often changes in response to atmospheric pressure changes, electromagnetic effects, or subtle environmental cues that humans miss. Birds may become restless before storms, dogs may seek shelter before earthquakes, and cattle may lie down before rain. While not always reliable, these behavioral changes reflect the sensitivity of living things to atmospheric conditions. The electromagnetic effects of approaching storms can be quite real. The electrical activity in thunderstorms can create changes in the local electromagnetic field that sensitive individuals might feel as tingling sensations or headaches. Some people report being able to feel storms coming hours before they arrive, possibly responding to these subtle electromagnetic changes or to the infrasound, low-frequency sound waves that storms can generate. Modern weather instruments have largely replaced these traditional methods of weather prediction, but they remind us that weather is not just a mechanical system, but a living process that affects and is affected by all forms of life. The atmosphere is not separate from the biosphere, but intimately connected to it, creating a complex web of interactions that scientists are still working to understand. Severe weather represents the atmosphere at its most energetic and dramatic. Tornadoes, those spinning columns of air that can reach wind speeds of over 300 miles per hour, are among the most intense weather phenomena on Earth. They form when specific conditions come together: strong wind shear, atmospheric instability, and a triggering mechanism like a cold front. The rotating updraft that creates a tornado can be incredibly powerful, capable of lifting and moving objects weighing tons. The tornado's characteristic funnel shape is created by the condensation of water vapor in the rapidly spinning air. The funnel itself is made visible by water droplets and debris picked up from the ground. Not all tornadoes produce visible funnels, and not all funnel clouds produce tornadoes that reach the ground. The classification system for tornadoes, known as the Enhanced Fujita Scale, rates them from EF0 to EF5 based on the damage they cause rather than their wind speed, since direct measurement of tornado winds is extremely difficult and dangerous. Hailstorms represent another dramatic manifestation of atmospheric energy. Hail forms in the strong updrafts of thunderstorms, where raindrops are carried high enough to freeze, then fall back down, accumulate more ice, and are lifted again. This process can repeat multiple times, creating layers of ice like an onion. The largest hailstones ever recorded were over 6 inches in diameter and weighed nearly 2 pounds, representing an enormous amount of energy in the atmosphere. The formation of severe weather often requires a delicate balance of atmospheric ingredients. Too little instability and storms won't develop. Too much wind shear and storms fall apart before they can organize. The most severe weather often occurs in what meteorologists call the Goldilocks zone of atmospheric conditions, where everything is just right for storms to develop and intensify. Predicting severe weather has become one of meteorology's greatest success stories. Doppler radar can now detect rotation in thunderstorms before tornadoes form, giving forecasters the ability to issue warnings with lead times that save countless lives. Satellite imagery provides a bird's-eye view of developing storm systems, while computer models can identify atmospheric patterns that favor severe weather development days in advance. Despite these technological advances, severe weather prediction remains challenging because of the small-scale processes involved. A tornado might affect an area only a few hundred yards wide, while weather models typically work with grid boxes that are several miles across. This is why local observations, storm spotters, and real-time monitoring remain crucial components of severe weather warning systems. The psychology of severe weather is as fascinating as the meteorology. Humans have evolved to fear severe weather, and for good reason. Our ancestors who took shelter during storms were more likely to survive than those who ignored the warning signs. Modern weather warnings tap into these deep-seated survival instincts, though the proliferation of warnings has led to some degree of warning fatigue in areas that experience frequent severe weather. Weather's influence on human mood and behaviour extends beyond the dramatic events to include subtle day-to-day effects. Studies have shown that people tend to be happier on sunny days, more aggressive during heat waves, and more prone to depression during prolonged periods of grey skies. The amount of sunlight we receive affects our production of vitamin D and influences our circadian rhythms, which can impact everything from sleep patterns to immune function. Seasonal affective disorder represents an extreme example of weather's impact on human psychology. During the shorter days of winter, some people experience significant depression that lifts when daylight hours increase in spring. Light therapy, which involves exposure to bright artificial light, can help alleviate these symptoms by mimicking the natural light that's missing during winter months. The cultural significance of weather varies dramatically around the world. Desert peoples have dozens of words for different types of wind, while Arctic cultures have multiple terms for various forms of snow and ice. These linguistic distinctions reflect the deep relationship between human cultures and their atmospheric environments. Weather becomes part of cultural identity, shaping not just practical activities like agriculture and construction, but also art, literature, and spiritual beliefs. Religious and spiritual traditions often incorporate weather as a manifestation of divine will or natural harmony. Rain dances, harvest festivals, and seasonal celebrations acknowledge the fundamental role that weather plays in human survival and prosperity. Many cultures view extreme weather events as carrying spiritual significance, whether as punishment, blessing, or message from the divine. Modern society's relationship with weather has become more complex as we've gained the ability to shelter ourselves from atmospheric extremes. Air conditioning and heating allow us to maintain comfortable indoor environments regardless of outside conditions. Transportation systems can operate in weather that would have isolated communities in the past. Yet this technological buffer can also disconnect us from natural rhythms and make us more vulnerable when systems fail. The increasing frequency of extreme weather events associated with climate change is forcing a re-evaluation of this relationship. Infrastructure designed for historical weather patterns may not be adequate for future conditions. Communities are having to adapt to new realities, from more intense hurricanes to unprecedented heat waves to changing precipitation patterns that affect water supplies and agriculture. Weather modification, the attempt to deliberately alter atmospheric conditions, remains a tantalizing but limited capability. Cloud seeding can increase precipitation under certain conditions, but the effects are modest and difficult to verify. More ambitious schemes to control hurricanes or prevent droughts remain in the realm of science fiction, limited by the enormous energy scales involved and our incomplete understanding of atmospheric dynamics. The ethics of weather modification raise complex questions about unintended consequences and competing interests. If one region uses cloud seeding to increase its rainfall, does that deprive downwind areas of moisture? Who has the right to alter weather patterns that cross political boundaries? These questions become more pressing as technology advances and climate change creates new pressures on water resources. Geoengineering, the deliberate large-scale intervention in Earth's climate system, represents the extreme end of human attempts to control atmospheric conditions. Proposed schemes include injecting particles into the stratosphere to reflect sunlight or fertilizing oceans to absorb more carbon dioxide. While these ideas might theoretically help address climate change, they also carry enormous risks and uncertainties that make them highly controversial. The study of weather on other planets provides fascinating insights into how atmospheric systems can develop under different conditions. Venus has a runaway greenhouse effect that creates surface temperatures hot enough to melt lead. Mars has dust storms that can engulf the entire planet for months. Jupiter's Great Red Spot is a hurricane-like storm that has been raging for centuries and is larger than Earth itself. These extraterrestrial weather systems remind us that Earth's atmospheric conditions are not inevitable, but the result of a delicate balance of factors including distance from the Sun, planetary composition, and the presence of liquid water. The more we learn about weather on other worlds, the more we appreciate the remarkable stability and habitability of our own planet's atmospheric system. Weather satellites, those artificial eyes in the sky, have revolutionized our understanding of global weather patterns. From their vantage point, hundreds of miles above Earth, they can see entire storm systems, track their movement, and measure atmospheric conditions that would be impossible to observe from the ground. The images they provide have become so familiar that we take for granted our ability to see Earth's weather from space. These satellites don't just take pictures. They measure temperature, humidity, wind patterns, and chemical composition of the atmosphere using sophisticated instruments. Some satellites focus on specific aspects of weather, like lightning detection or precipitation measurement. Others provide the broad overview that helps meteorologists understand how regional weather patterns fit into global circulation systems. The data from weather satellites feeds into the computer models that generate our daily forecasts. These models solve mathematical equations that represent the fundamental physics of atmospheric motion, requiring some of the world's most powerful supercomputers to process the enormous amounts of information involved. The fact that we can predict weather several days in advance with reasonable accuracy represents one of humanity's greatest computational achievements. Yet for all our technological prowess, weather forecasting remains fundamentally limited by the chaotic nature of atmospheric systems. Beyond about 10 days, detailed predictions become increasingly unreliable. Not because our computers aren't powerful enough or our measurements aren't precise enough, but because the atmosphere itself is inherently unpredictable over long time scales. This limitation isn't a failure of science, but a fundamental property of complex systems. A reminder that some aspects of nature will always retain an element of mystery. The art of weather observation continues to evolve, blending traditional techniques with cutting-edge technology. Automated weather stations now collect data continuously from remote locations, while storm chasers armed with portable instruments venture into severe weather to gather measurements that satellites and radar cannot provide. Citizen scientists contribute observations through networks of volunteer weather watchers, creating a global community of sky observers who help fill in the gaps between official monitoring stations. Amateur meteorologists often develop remarkably keen skills at reading the sky, learning to interpret subtle cloud formations, wind shifts, and atmospheric pressure changes that might escape casual notice. They understand that weather is not just data points and computer models, but a lived experience that unfolds in real time across the landscape. Their observations remind us that despite all our sophisticated instruments, there's still value in simply watching the sky with educated eyes. The language of weather is rich with poetry and precision, from the technical terms that meteorologists use to describe atmospheric phenomena to the folk expressions that capture weather's emotional impact. Words like nimbus and cumulus carry both scientific meaning and aesthetic beauty. Phrases like mackerel skies and mare's tails describe cloud formations with vivid imagery that helps us remember their characteristics. This linguistic richness reflects humanity's long relationship with atmospheric conditions and our need to communicate about weather's infinite variations. Weather's influence on agriculture extends far beyond the obvious need for water and warmth. Farmers must consider not just how much rain falls, but when it falls, not just average temperatures, but the timing of frosts and heat waves. The relationship between weather and crops is so intimate that experienced farmers can often predict weather patterns by observing plant behavior. Leaves that curl inward might signal approaching dry conditions, while certain flowers that close their petals could indicate rain is coming. The development of agriculture itself was fundamentally shaped by regional weather patterns. Different crops evolved to thrive in specific climatic conditions, and human societies adapted their farming practices to match local atmospheric rhythms. The monsoon patterns of South Asia gave rise to rice cultivation, while the Mediterranean climate fostered olive trees and grapevines. These agricultural adaptations in turn influenced cuisine, trade patterns, and cultural traditions that persist to this day. Modern precision agriculture uses increasingly sophisticated weather monitoring to optimize farming decisions. Sensors in fields measure soil moisture, temperature, and humidity at multiple depths and locations. Drones equipped with cameras and instruments can assess crop health and weather damage across large areas. Farmers can receive alerts on their smartphones when conditions are optimal for planting, spraying, or harvesting, turning weather data into actionable information that can significantly improve yields and reduce waste. The tourism industry represents another sector deeply intertwined with weather patterns. Ski resorts depend on winter snowfall, beach destinations rely on sunny skies, and adventure tour operators must constantly adapt to changing atmospheric conditions. Weather affects not just where people choose to travel, but when they travel, how they pack, and what activities they can enjoy. Some destinations have built their entire economies around specific weather patterns, making them particularly vulnerable to climate variability. Weather photography has emerged as its own art form, with photographers pursuing dramatic storms, capturing the delicate beauty of frost patterns, or documenting the play of light through clouds. These images help us see weather not just as a practical concern, but as a source of visual wonder. Time-lapse photography reveals the dynamic nature of atmospheric processes, showing how clouds form and dissipate, how storms develop and move, how the sky transforms from moment to moment. The sounds of weather create their own atmospheric symphony. The gentle patter of light rain on leaves differs from the sharp percussion of heavy drops on pavement. Wind through pine trees makes a different sound than wind through oak leaves. Thunder can range from sharp cracks to rolling rumbles depending on the distance and type of lightning. These acoustic signatures help us identify weather conditions even when we can't see the sky, adding another dimension to our atmospheric awareness. Indoor air quality represents an often overlooked aspect of weather's influence on daily life. Outdoor atmospheric conditions affect what enters our homes and workplaces through ventilation systems and open windows. High humidity can promote mold growth, while very dry air can cause respiratory irritation. Barometric pressure changes can affect how buildings settle and how doors and windows fit in their frames. Even our indoor environments remain connected to the vast atmospheric system outside. The field of biometeorology studies how weather affects living organisms. From the microscopic to the massive, plants time their flowering to atmospheric cues, insects adjust their activity patterns to pressure changes, and animals migrate in response to seasonal weather shifts. These biological responses to weather have evolved over millions of years, creating intricate relationships between atmospheric conditions and life cycles that we're still discovering. Human sensitivity to weather changes varies dramatically from person to person. Some individuals seem almost immune to atmospheric variations, while others experience significant physical and emotional responses to pressure changes, humidity shifts, or electrical activity in the atmosphere. This variation might reflect genetic differences, past experiences, or simply different levels of attention to environmental cues. Understanding these individual differences helps explain why weather affects people so differently. The emerging field of weather psychology explores how atmospheric conditions influence human behavior, decision-making, and mental health. Researchers have found correlations between weather patterns and everything from crime rates to consumer spending, from academic performance to relationship satisfaction. While these connections are often subtle and complex, they suggest that our psychological lives remain more connected to natural rhythms than we might realize in our climate-controlled world. Weather disasters often bring out both the worst and the best in human nature. The same storm that causes destruction and suffering can also inspire remarkable acts of courage, generosity, and community cooperation. People who might never speak under normal circumstances come together to help neighbours, share resources, and rebuild damaged communities. These experiences remind us that weather is not just a physical phenomenon, but a social force that can strengthen human bonds and reveal our capacity for resilience. Recovery from weather disasters often takes much longer than the events themselves. A hurricane might last for hours, but rebuilding can take years. A drought might persist for months, but its economic and social effects can linger for decades. These long-term impacts highlight how deeply weather is woven into the fabric of human society, affecting not just immediate safety and comfort, but long-term prosperity and development. Climate adaptation is becoming an increasingly important aspect of community planning as weather patterns shift and extreme events become more frequent. Cities are redesigning infrastructure to handle more intense rainfall. Coastal communities are preparing for higher storm surges, and agricultural regions are developing new crops and techniques to cope with changing precipitation patterns. These adaptations require not just technological solutions, but social and economic changes that help communities become more resilient. Traditional ecological knowledge accumulated by indigenous communities over generations offers valuable insights into local weather patterns and their variations. These communities often have sophisticated understanding of atmospheric cycles, seasonal changes, and the relationships between weather and ecosystem health. Their knowledge systems provide important perspectives on climate adaptation and sustainable relationships with atmospheric resources. The democratization of weather information through smartphones and the internet has transformed how people interact with forecasts and atmospheric data. Instead of waiting for scheduled weather broadcasts, people can access real-time conditions, radar imagery, and detailed forecasts anytime they want. This constant availability of weather information has changed how we plan activities, make travel decisions, and prepare for severe weather events. Social media has created new ways for people to share weather experiences and observations. Photos of dramatic clouds, reports of local conditions, and real-time updates during severe weather events create a distributed network of weather communication that supplements official forecasting services. These informal networks can provide valuable local information that helps communities respond to rapidly changing conditions. Weather apps and services now offer increasingly personalized forecasts that consider individual preferences, activities, and sensitivities. Some apps provide alerts for conditions that might affect outdoor exercise, notify users when air quality might impact respiratory health, or suggest optimal times for activities like gardening or photography. This personalization reflects growing recognition that weather affects everyone differently, and that useful forecasts must account for individual needs and circumstances. The gamification of weather awareness through apps and websites that reward accurate predictions or encourage weather observation has created new forms of citizen engagement with atmospheric science. People compete to make the best forecasts, share interesting weather photos, or contribute observations to research projects. These activities help build weather literacy and create more informed communities that can better prepare for and respond to atmospheric hazards. Educational approaches to weather and climate science are evolving to help people understand not just what weather is, but how it connects to broader environmental and social systems. Interactive simulations allow students to experiment with atmospheric conditions and see how changes affect weather patterns. Virtual reality experiences can provide immersive encounters with severe weather that would be too dangerous to experience directly. These tools help build the kind of atmospheric literacy that citizens need to make informed decisions about climate-related issues. Weather's role in shaping human settlement patterns continues to evolve as technology allows people to live in increasingly challenging environments. Air conditioning makes hot climates more habitable, while improved heating systems extend comfortable living into colder regions. Flood control systems and hurricane-resistant construction allow communities to persist in areas prone to severe weather. Yet these technological adaptations often require enormous energy inputs and can create new vulnerabilities when systems fail. The insurance industry has developed sophisticated models for assessing weather-related risks, using historical data and climate projections to estimate the likelihood of various types of atmospheric damage. These risk assessments influence everything from individual insurance premiums to large-scale development decisions. As weather patterns change, insurance companies are having to constantly update their models and adjust their coverage policies, creating economic pressures that can drive adaptation in other sectors. Weather derivatives represent a financial innovation that allows businesses to hedge against weather-related risks. A farmer might purchase a contract that pays out if rainfall falls below a certain threshold, while a utility company might buy protection against unusually warm winters that reduce heating demand. These financial instruments help transfer weather risk from those who are directly exposed to those who are better positioned to bear it. The concept of weather equity has emerged as communities recognize that atmospheric hazards don't affect everyone equally. Low-income neighbourhoods often have less tree cover and more heat-absorbing surfaces, making them more vulnerable to extreme temperatures. Communities with limited resources may have less access to air conditioning, flood protection, or early warning systems. Addressing these disparities requires considering weather impacts as part of broader social justice concerns. International cooperation on weather and climate issues reflects the global nature of atmospheric systems. Weather patterns cross national boundaries without regard for political divisions, making international collaboration essential for effective forecasting and climate adaptation. Organizations like the World Meteorological Organization coordinate global weather observation networks and facilitate the sharing of data and expertise that benefits all nations. The future of weather prediction may involve artificial intelligence systems that can identify patterns in atmospheric data that human forecasters might miss. Machine learning algorithms are already being used to improve precipitation forecasts and severe weather warnings. As these systems become more sophisticated, they might be able to extend the useful range of weather predictions or provide more accurate forecasts for specific locations and applications. Quantum computing represents another frontier that might revolutionize weather prediction by allowing meteorologists to solve atmospheric equations with unprecedented precision and speed. These advanced computers might be able to model atmospheric processes at much finer scales, potentially improving our ability to predict local weather conditions and severe weather events. However, the fundamental chaotic nature of atmospheric systems will likely continue to limit long-term predictability regardless of computational advances. The integration of weather information with other environmental data streams is creating new opportunities for understanding how atmospheric conditions interact with air quality, water resources, ecosystem health, and human activities. These integrated approaches recognize that weather is not an isolated phenomenon but part of complex environmental systems where changes in one component can cascade through others in unexpected ways. Personal weather stations and environmental sensors are becoming increasingly affordable and sophisticated, allowing individuals to monitor atmospheric conditions around their homes and businesses with scientific precision. These devices can measure not just temperature and humidity, but also air quality, UV radiation, soil moisture, and other environmental parameters. The data they collect contributes to our understanding of local weather patterns and helps people make more informed decisions about outdoor activities and environmental health. Weather's influence on renewable energy production adds new dimensions to atmospheric forecasting. Solar power output depends on cloud cover and atmospheric clarity, while wind power generation requires accurate predictions of wind speed and direction. As societies transition toward renewable energy sources, weather forecasting becomes not just a matter of comfort and safety, but also economic and energy security. The study of atmospheric rivers, those narrow bands of moisture-laden air that can transport water vapor across vast distances, has revealed new insights into global precipitation patterns. These invisible rivers in the sky can carry more water than the Amazon River, and when they encounter mountains or other lifting mechanisms, they can produce intense precipitation events. Understanding atmospheric rivers is crucial for predicting both drought and flood conditions in many regions. Urban weather networks are providing unprecedented detail about atmospheric conditions within cities, revealing how temperature, humidity, and air quality can vary dramatically across neighborhoods. These fine-scale observations help urban planners understand heat island effects, optimize placement of parks and green spaces, and design buildings and infrastructure that work with, rather than against, local atmospheric conditions. The relationship between weather and mental health continues to be explored through research that examines how atmospheric conditions affect mood, cognitive function, and psychological well-being. Some studies suggest that certain weather patterns might influence the timing of mental health episodes, while others explore how access to pleasant weather and outdoor spaces affects overall psychological health. This research has implications for urban design, healthcare planning, and individual wellness strategies. Weather's role in shaping cultural identity extends beyond practical adaptations to include spiritual and artistic expressions that reflect deep relationships with atmospheric conditions. Rain ceremonies, harvest festivals, and seasonal celebrations acknowledge the fundamental role that weather plays in human life. These cultural practices often contain sophisticated understanding of local weather patterns and their variations, passed down through generations of careful observation. As our exploration of weather's vast realm draws toward its gentle close, we find ourselves with a profound appreciation for the invisible ocean that surrounds us every moment of our lives. Weather is far more than the daily forecast or the conditions outside our windows. It's the breath of our planet, the circulation system that connects every corner of Earth, the dynamic force that has shaped the evolution of life itself. From the smallest water droplet forming on a blade of grass to the mightiest hurricane spinning across ocean basins, weather operates across scales that challenge our imagination. It connects the microscopic processes happening in cloud droplets to the planetary scale circulation patterns that distribute heat and moisture around the globe. It links the breath you just took to the vast atmospheric currents that have been flowing for billions of years. Understanding weather helps us understand our place in the natural world. We are not separate observers of atmospheric phenomena, but participants in the grand circulation of air and water that makes our planet unique. Every breath connects us to this system. Every step outside places us within currents of air that have travelled thousands of miles, carrying with them the stories of distant places and the promise of future weather. The next time you feel the wind on your face, watch clouds drift across the sky, or listen to rain falling outside your window, remember that you're witnessing one of the most beautiful and complex systems in the universe. Weather is nature's poetry written across the sky, a constantly changing artwork painted with air and water, light and shadow, warmth and coolness. As you drift towards sleep tonight, perhaps listening to the gentle sounds of weather outside, let yourself be cradled by the knowledge that you rest within this vast atmospheric embrace. The air that surrounds you has travelled the world, carrying the breath of forests, the moisture of oceans, the warmth of sunshine. You are held safely within this invisible ocean that connects all life on Earth. Tomorrow will bring new weather, new combinations of atmospheric conditions that have never existed before and will never exist again in exactly the same way. Each day offers its own unique atmospheric signature, its own blend of temperature and moisture, pressure and wind. Weather ensures that no 2 days are ever truly identical, that our world remains dynamic, surprising, and endlessly fascinating. Sleep well, fellow traveller, knowing that while you rest, the atmosphere continues its endless dance. Somewhere clouds are forming while others dissolve, winds are shifting direction, and moisture is cycling from sea to sky to earth and back again. You are part of this magnificent system, breathing with the planet, sharing in the great circulation of life itself. And when you wake, step outside with new eyes to see the miraculous, ordinary magic of weather. Feel the air against your skin and know that you're touching the breath of the world. Look up at the sky and see not just clouds, but the visible expression of invisible forces. Listen to the wind and hear the planet singing its ancient song of circulation and change. For in understanding weather, we discover that we are never truly alone. We are always surrounded by this vast, dynamic ocean of air that connects us to every other living thing, every distant shore, every mountain peak and valley floor. Weather reminds us that we live not on a static rock in space, but on a breathing, dynamic world where everything is connected to everything else in the grand dance of atmosphere and life. Sweet dreams, and may the gentle rhythms of weather carry you softly into peaceful slumber, knowing that you are forever held within the loving embrace of our planet's atmospheric heart.